All right, in activity 2.2, we're going to be looking at another type of pattern. So it says analyze the pattern that we have going from day 1 to day 2 to day 3, and then on the side here it goes in that order of the days. It says complete the table to summarize the number of seniors who learned about the election results each day. Then write an expression to represent the number of seniors who learned about the election results on the nth day to keep it going if we wanted to. Finally, describe how each part of your expression relates to the visual model. So on day 1, it looks like we start with 3 seniors. On day 2, we have 2, 4, 6 seniors. Okay, on day 3, we have 2, 4, 6, 8, 10, 12 seniors. So if you notice, it looks like we are kind of multiplying by 2 each time. So my next one would be 24. Then we got 48. Then we have 96. Okay, so we have to try to create an equation. Well, if I'm multiplying by 2, that's a little bit like geometric. So let's try to make a geometric equation, because each time if we're multiplying by 2, then we know we're going to keep increasing by that 2. So my geometric equation, remember, for explicit, a sub n equals a sub 1 r to the n minus 1. So a sub n equals the first term, or the first amount of people we had was 3. My r that we're multiplying by is 2 to the n minus 1. So I can go ahead and write that in there. So 3 times 2 to the n minus 1. It says create a graph of the data from your table on the coordinate plane shown. Then draw a smooth curve to model the relationship between the number of days that pass and the number of seniors who hear the senior election results that day. Okay, so day 1 we had 3. Which should be, so it looks like it's going up in increments of 10, so pretty close to the bottom there. Day 2 is 6, so just a little bit higher. It's hard to draw dots on this. Day 3 is 12, so now we can bump across that 10 mark. Day 4 is 24. Okay, day 5 is 48. So close to that other mark there, because it's going up by 10, so that would be close to my 50 mark. And day 6 is 96. So somewhere like right there. So it looks like that. It says, do all the points on the smooth curve make sense in terms of the problem situation? Why or why not? The problem that we don't talk about in this is half days. We are going up in increments of, sorry, that should say half. We're going up in increments of 1, 2, 3, 4, 5, 6, 7, 8. You only have real whole numbers as points on the graph. We don't have any negative sides to it. Okay, so it's a little bit different. It's all the points on the smooth curve do not make sense in terms of this problem situation, because the number of days represent discrete data values. Only integers greater than or equal to 1, meaning we don't have decimals, we don't go negative, to make sense in terms of this problem situation. All right. Describe this pattern as linear, exponential, or quadratic. Well, if you look at it, it has the variable in the exponent, so it's going to be an exponential. Variable in exponent, and it's got the same increasing base each time. All right, after how many days will 500 new students learn about the election results? I just realized I put this in the wrong section. So this whole thing should be up here. So I'm going to erase it so that I can answer question 4. All right, question 4. Describe the key characteristics of your graph. Explain each characteristic algebraically in terms of this problem situation. Okay, so when it's talking about describing different characteristics of the graph, what we're looking for are the shapes of it, the intercepts of it, and stuff like that. So if we look, the shape of it is a curve shape, so I could say it's an exponentially curved shape. So I'm going to write that one in first. Okay, now let's look at its intercepts. So remember, my x-axis is this guy here. it doesn't look like we have an x-intercept or really a y-intercept because we started on day 1. We didn't start on day 0. Okay, if we would have a y-intercept and I wanted to find it, one way to do it is, well, if you don't remember how to find a y-intercept, pick some points on your y-axis. So like if I picked this point right here, that would be 0, 10. If I picked this point here, it would be 0, 40. If I picked this point right here, it would be 0, 60. One thing that you notice is all the x values don't change. They're all zeros. So if I plug 0 in for x, I'll be able to find where it's hitting my y-axis if that was something I wanted to look for. So if we go up here and we type in y equals 3 times 2, I plug in 0 for what the x value would be, so in this situation it's the n value, and then type this in your calculator. Make sure when you do the caret button to get that 0 minus 1, that either you type in -1, because that's what 0 minus 1 is, or you have to use parentheses to say they're up together in the exponent. Okay, and then you should get 1.5. So the y-intercept, if we had one, was 0, 1.5. But we don't start on day 0. Okay, after how many days will 500 new students learn about the election results? Okay, you could do a little trial and error. So if I wanted to do it, I could say y equals 3 to the 2. We could try 8 first. Type that in my calculator, and we're trying to get closer and closer to 500. That gets me 384, so I'm going to try one more higher and see if it gets me a little bit closer. So I'm going to throw a 9 in there, so my 9th day, so 3 to the 2, 3 times 2, and then 9 minus 1. Okay, that gives me 768, so it's in between my 8th and 9th day that they would be learning the election results. Okay, determine the number of seniors who heard their election results on the 12th day. So now all we have to do is plug in 12 to figure out how many seniors would learn on the 12th day. So 3 times 2 to the power of 12 minus 1, or you could just type in 11 there. Okay, we would have 6,144 seniors that would know. Does it make sense in the context of this problem? At some point, the seniors should stop. You probably don't ever have 6,000 seniors. So no, it really doesn't make a whole lot of context to it because at some point there are going to be no more new seniors. So you could say no because at some point it should stop. We shouldn't have that many seniors. All right, 2.3, increasing and decreasing pattern. So describe the pattern as linear, exponential, or quadratic. Explain your reasoning. So you're trying to see different patterns in it that's happening. So one thing I would do is I would add totals. I would see what other shapes does it kind of look like that I can compare it to. So what I'm going to do is I'm going to write my sentences down of a couple of things that I noticed, and then I'm going to talk about it. So I'm going to pause the video and write those down. All right, so first I did totals. I added the first one, I got 5 boxes. The next one I got 10 boxes. The next one I got 17 boxes. Okay, another thing I noticed is I could technically make them all squares if I closed in and had some extra white boxes. I noticed that the design number, so design 1 is n plus 2 boxes. So like if I was trying to get this is a 3 by 3, this is a 5 by 5, and a 7 by 7. If I looked at that design number there and did it, and I added 2 to it each time, I would get my dimensions. And when I mean dimensions of my colored boxes. So if I look in here, this would get me n plus 2, this would get me n plus 2, this would give me n plus 2. So you probably didn't see that one because I had a little help with the book on that one. Okay, so then it says describe how each term in Maureen's expression represents the visual model. So I need to figure out how this n plus 2 squared minus 2 times n plus 1 comes into play. So I'm going to go ahead and erase some of my drawings here. And I realized what would have made more sense is if I didn't mess this up. So this actually was a 4 by 4 and a 5 by 5. Okay, so this n plus 2 that's happening, if we're squaring, generally that means we're doing the area of the box. So this is the total area of my box. Okay, so when we do the total area of the box, it says n plus 2 squared. So n plus 2, I kind of talked about it earlier, but I messed up this 4 and this 5 here. N plus 2, n is the design number. N is design number. Oop. Okay, so if I take my design number and add 2 to it, I get the fact that it's going to be a 3 by 3, and we square it to get the total set of boxes. My next one, I already have this. I need to get to 4. If I add 2 to it, we square it to get our total area. My next one, design 3. If I want my total area, I add 2 to it, and then we square it, because base times height gets me that squared. Okay, but the problem is I don't want the whole thing. I got to take away all of those white boxes. So when we look at the white box totals here, so if I erase, we just found the total of the entire thing. My white box total, I have 2 white boxes right here. How do I get from the design number to the fact that there are 2 white boxes here? Well, it adds 1 that time. Let's check to see if that's the pattern. I add 1 that time. And I add 1 that time. Okay, so if I'm adding 1 each time, I could say n plus 1, because n is my design number, but there are 2 sets of them, because we got both corners. So that's why there's a little 2 that is sitting in front. So this is subtracting all the white boxes out. All right, so it says consider Matthew's expression, n squared plus 2n. Use technology to verify graphically the equivalence of 2 expressions. So what you need to do is you need to get your graphing calculator. The people that don't have graphing calculators, you will need to have one for the test, because there is a graphing calculator question in the test. Otherwise, you can go to desmos.com and you can type these things in. Okay, so my graphing calculator people, you're going to turn your calculator on. If you have not graphed before, you're going to press your y equals button, and then your y sub 1 should be the first thing that pops up. Okay, so the next thing you need to do is you need to press x squared. So you can either use the squared symbol or you could use the caret and the 2. Your x button is in like the top left hand corner by your second alpha, your mode. It's right underneath your mode. So you're going to type in x squared, and then you're going to type in plus 2. You're going to press that x button again, plus 2. And then in the top right of your calculator, there's this big graph button where it says graph. It's below blue table. You're going to graph it. Okay, so then the next question, it says identify the parts of the graph that represent this problem situation. Okay, the problem in this one is, do we want any of the negatives? No, we didn't talk about negative boxes. Okay, we shouldn't go negative in this. So the only parts of this is the positive side. Okay, it should look like a U. So in this situation, if I were to kind of do it a little bit here, yours should look close to that. Okay, verify the equivalence of the 2 expressions algebraically. So in the last person's, we had n plus 2 squared minus 2 times n plus 1. And then we have Matthew's, which was n squared plus 2n plus 2. Okay, remember squared tells me I have to write it out twice. N plus 2, n plus 2, and then I have to distribute. So n times n gets me n squared, n times 2 is 2n, 2n, 4. So you distribute the first set to the back parentheses, the second set to the back parentheses, and now I distribute negative 2. So I get negative 2n minus 2. The negative goes with it. Okay, then I can go ahead and combine like terms. So if I combine, I've got these are all my n's. So 2n plus 2n is 4n, minus 2n is back down to 2n. So I have n squared plus 2n, and then 4 minus 2 gets me 2, which is the same as what Matthew had. Okay, so to accommodate outdoor furniture, a grill and a shed, The patio must have an area of at least 125 square feet, not including the walkways. What is the smallest design math you can build and still have enough space for these items? Okay, so the easiest equation to probably plug into is going to be, to keep the pattern going, Matthews, because it's a lot less work. So we're going to create this table. So this is going to be my design number. And this is going to be Matthew's equation. So n squared plus 2n plus 2 to see the closest one that we can get to for the 125. Okay, so then I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to do 10, 11, 12 over here. I'm going to run out of space. All right, so what you need to do is pause the video and type in 1 into the calculator, 2 into the calculator, 3, and you're typing it in for both ends. So for example, the first one, whenever I take out a letter and put in a number, I want to make sure I use parentheses. So when I type it in my calculator, I type in the 1 for both of those ends and I use parentheses, because if it was a negative, it could change something. Okay? Or another thing you could do is, if you still have your graphing calculator, is if you press your second button, which is in the top left-hand corner, and then you click the one that says graph, says table above it, you should get all of your table values. So if I look at 1, I have the answer to 1. 1 is going to be 5. I don't even have to plug it in, because my equation is still in my line spot. So 2 is 10, 3 is 17, 4 is 26, and then I could keep going. 5 is 37, and then I'm going to go ahead and just quickly go through these because I'm looking at my table. All right, so I'm kind of finish it out. So it says, to accommodate the outdoor furniture, a grill, and a shed, the patio must have an area of at least 125. So he has to be at least at design 11 to be able to create this outdoor patio. Here is another double check that I would definitely write down to show that this equation is going to be quadratic. If you take the fact that this said 5, 10, 17, which is from our original page, if I go back, our pattern was we added 5, 10, 17. If you take the difference, you should be getting a pattern with that. I'm going to show you once I go back. Oop, too far. If I take 5 or 10 minus 5, I get 5. 17 minus 10, I get 7. So I'm taking the difference, so I'm subtracting. 26 minus 17 is 9. Here, I'll do it different colors. Okay, 50 minus 37. I messed up this green one. Ooh. This 9 should be up higher. This is the 9. Okay, there we go. 11, 13, 15. Okay, there's my first difference. Now if I do my second difference, I get 2, 2, 2, 2, 2, and it would keep going. So to know it's an exponential equation, if you take your pattern and do the second difference of it, you're going to get that common number every single time. So if you can get your total pattern and keep adding them like it is, take the difference of it twice, you're going to see that common pattern of 2 or common pattern in it, okay? And then you should realize that it's going to be a quadratic. It's going to work every single time for the quadratic. So I would write that down in my notes. The second difference is a common number, and that tells me it's a quadratic. Okay, it says describe the similarities and differences among linear, exponential, and quadratic functions. So I would write down the fact that lines are going up by a constant term. You're adding the same thing each time. Exponential has a base number. You're multiplying the same thing each time to get that base to continue and get that exponential growth. Quadratic, the second difference is always going to be that constant number.